In approx 30 minutes, you're going to build your very first Breakout game in Unity, and it's going to look like this. We're not just copying pasting. I'm going to show you how to write clean, modular code so you can actually modify and expand your level later. We'll even add those satisfying visual effects that make a game feel finished. You can code along with me, step by step. Or if you want the full project file right now, you can grab them for just $1, link in description, to support the channel. Keyboard ready? Let's dive in. Open a new 3D project in Unity and create 3 folders: Prefabs, Scene, and Scripts. Start by creating a scene. Right-click on the Scene folder, create Scene. Name it Brick Breaker and double-click it. You can see that it already contains a camera and a light. Next, create a reusable brick model. In Unity, this is called a prefab. Right-click on the Prefab folder, create Scene Prefab. Rename it Brick and double-click it to edit it. For now, the prefab is an empty object with only a transform component. Components are small specialized scripts to attach to objects in a scene. We'll see several that come directly from the engine and create others ourselves. Create a visual for the brick with a right-click, 3D object, cube, rename it Skin. You can see that the cube comes with pre-established components: a transform that manages position in space, a mesh filter that provides shape information, a mesh renderer that displays the object in the scene. You can remove the box collider at this level since it is useless in our case. At this point, you have a prefab with 2 levels of depth: the root and the child. Keep this structure in mind, we will use it along the tutorial. What we want to achieve with this structure is to separate gameplay logic from visual logic. Gameplay logic, like positioning or collision detection, should always be applied to the root. Visual logic, like animation, should be applied to the child. This way, your gameplay will always be preserved regardless of the visual effect you add in the future. To detect when the brick is hit, add a box collider component to the root. Move the collision box by 0.5 on each axis so that the pivot point of the prefab is at the bottom left. Also, move the child by 0.5 on each axis and reduce its scale to 0.9 to create visual spacing on each side. Now, let's create the brick class. Right-click on the script folder, create Scripting, MonoBehavior script and rename it Brick. Double-click to edit it. The goal is to have bricks with 1 or more hit points, that their color represents this number of hit points, and that they are destroyed when they reach 0. We will also have immortal bricks, like those that surround the level. Start by indicating the required component, here a box collider. Then expose a few public variables that you can define directly in the inspector. You can organize them by displaying headers like this. You need a reference to the skin object, a color for immortal bricks, a list of colors for the other bricks. Then public variable but hidden from the inspector. The current number of hit points, whether the brick is immortal. To communicate specific events to other scripts, we use actions. Create one to indicate that the brick is touched with the new display color as parameter, and one when the brick is destroyed. Finally, a private reference to the box collider. Create a function init that takes an integer as parameter. Use this parameter to initialize the number of hit points. We will say that if the number of hit points is -1, then it is an immortal block. Also, assign the starting color of the brick. To do this, retrieve the renderer of the skin object, access its material, and change the color to the one returned by getColor. We use getComponent to retrieve the box collider. Since this function is costly in resources, we keep the reference in memory to access it faster. The getColor function returns a color based on the brick hit points. If they are equal to -1, it is the color of immortal bricks. Otherwise, we need to do a small check. The first index of list is index 0, but our first living brick has at least one hit point. So you will get the color at the index equal to the number of hit points -1. However, the color list is filled manually in the inspector, so we might not have added enough color. We check if this index exists, and if not, we throw an error. The damage function takes a number of damage points as parameter. Subtract this number from the hit point, unless it is an immortal brick, in which case subtract 0 instead. If at least one other script listens to the untouched event, propagate it with the new required color. If the brick reaches 0 hit point, disable its box collider so it can no longer affect the board. If another script listens to the undie event, propagate it, otherwise destroy the brick immediately. The die function destroys the brick. Return to the editor, add the brick component to the prefab, reference the skin, choose a color for immortal brick and 4 colors for normal bricks. We want a simple way to organize our bricks to compose levels. Right-click on the script folder, create scripting empty C# script and name it level definition. Double-click to edit it. Make it a static class so you can access it globally, and create your first level as two-dimensional integer array. The -1 represents immortal bricks. The 0, empty spaces. 1, 2, 3 and 4 are normal bricks and their hit points. You can play with this to create pixel art style drawings. Note that I did not put the -1 around the level. Since all level will be surrounded by immortal bricks, we will add them directly in code to save time when creating level. Now, we will use this level definition to assemble the brick in the game. Right-click on the prefab folder, create scene prefab and name it level. Then, the associated script, right-click on script, create scripting monobehavior script and name it level. Double-click to edit it. Inside, expose several public variables hidden from the inspector. A reference to the brick prefab, a height and a weight. Define a first function, createBrick, that takes a position and a number of hit points. Instantiate the brick prefab, forcing the given position, default rotation and transform component of the level object as parent. Initialize it. Your init function takes a two-dimensional array and a reference to the brick prefab. Store the reference, retrieve the weight and height of the array. Start by creating the outer borders. For vertical borders, iterate from -1 to level height +1. Each time, create an immortal brick on the left and right side. Note that I position the level on the X-Z axis, so I map the Y-axis of my 2D array to the Z-axis of my 3D world. For horizontal borders, iterate from -1 to wide +1 and create immortal bricks at the top and bottom. Then, iterate over your two-dimensional array, retrieve the value at X and Y. If the value is 0, it is an empty space, so skip it. Otherwise, create a brick. Note that here, you need to invert the Z position so that the first row of your array appears at the top of the level, not the opposite. Go back to Unity and attach this component to the level prefab. Now, we just need a link between all these elements. For that, we will create a context that will act as the orchestrator. Directly in the scene, right-click, create empty, and rename it context. Then, right-click on Scripts folder, create scripting monobehavior script, and name it context. This component will require several references from the inspector: the camera, the brick prefab, the level prefab, and it will keep a private reference to the level it creates. In the awake function, which is automatically called by Unity at scene startup, we retrieve our level definition and load it into a level. The loadLevel function takes the level definition as parameter. It calls createLevel and stores the reference to the created level, then positions the camera based on the level size. The value I use here work with my level size. If you have different shape, you will need to adapt the position. The createLevel function takes the level definition as parameter, instantiates the level, initialize it by passing the reference it needs, and returns the instance. Attach the context script to the context object, provide the required reference, and click play to see the result. We will make this a bit nicer with background bricks. Same principle as for the brick. Right-click on Prefab, create scene prefab, and name it BackgroundBrick. Right-click, 3D object, cube, and name it skin. Remove the box collider, then create the associated script, background script. Define a reference to the skin and a list of possible colors. In Awake, retrieve the renderer component and randomly change the material color using one of the available colors. Return to Unity, attach the component to the prefab and define the variable. Then open the level class. Add a reference to BackgroundBrick and create a function, createBackgroundBrick, that takes a position. Instantiate the prefab with the given position, default rotation, and the level transform as parent. Modify init function to request this reference, store it, and iterate over the level, width, and height to create background bricks. Note that we position them at -1 on the y-axis. Modify the context class, add a reference to BackgroundBrick, and pass it during level initialization. Return to Unity, pass in the prefab, and click play. The next step is to add a paddle that the player can control by moving it from left to right. Using the same approach, create a new prefab. Right-click on the Prefabs folder, create Scene Prefab. Name it Paddle. At the root, add a box collider, moved by 0.5 on each axis, and a child skin moved the same way and without a box collider. Create the associated component, right-click on the Scripts folder, create Scripting monobehavior script and name it Paddle. Start by indicating to Unity that the box collider component must also exist on the object. Then, define variable editable from the inspector for the reference to the skin, the paddle size, its speed, and its color. Also define an action when the paddle moves with vector-free parameter, as well as an action when the paddle is hit by the ball, also with vector-free parameter. Finally, two private variables for movement limits. In the awake function, apply the color to the skin and apply the correct size. The changeLimit function simply defines the movement limit of the paddle. The touch function will be used by the ball when it hits the paddle. It checks if at least one script is listening for this event, and if so, it propagates it. The move function takes a direction and the number of seconds elapsed since the last frame. It calculates the distance traveled, retrieves the current position of the paddle, and computes its next position by adding the direction multiplied by the distance. It checks if the next position is outside the defined limit, and if so, corrects the value. by subtracting the current position from the next position, you will get the offset difference, which you propagate through the onMove event if at least one script is listening. Apply the change. In the update function, we listen for user input. If the left arrow key is pressed, we call the move function with the vector pointing to the left. If it's the right arrow key, with the vector pointing right. Return to Unity, attach the script to the paddle prefab, and fill in the required field. Open the context script, add a reference to the paddle prefab, create a createPaddle function that instantiates the paddle and applies the limit defined by the current level. Finally, modify the load level function to include the paddle creation step. Return to Unity, assign your paddle reference and click play. You now have a paddle that can move left and right. Next step, the bar. Create a new prefab, right-click on Prefabs folder, create, scene, prefab and name it bar. This time, we will keep the pivot point at the center. Add a skin using right-click, 3D object, sphere. Remove the sphere collider, we don't need it. Note that we also do not add a collider to the root, because we will detect ball collision using ray casting. Right-click on the script folder, create scripting monobehavior script. Expose in the inspector the reference to the skin, the ball color, its starting speed, and an acceleration value. Then define 3 actions: when the ball is launched, when it hits something, and when it's destroyed. Add a private reference to the paddle and the current state of the ball. The init function stores the reference to the paddle and applies the color to the ball. If the ball is not yet launched, it is still attached to the paddle, so we want it to move along with it. To do this, we listen to the paddle onMove event and assign it a callback. This callback calls our internal function followPaddle. If the ball is already launched, we call the launch function instead. In all cases, we call the redirect function. The followPaddle function moves the ball by the same offset as the paddle. The launch function stores the ball state, removes the callback from the onMove event so the ball stops following the paddle, and propagates the onLaunch event if at least one script is listening. The redirect function takes a position and a direction, reposition the ball and rotate it so that the z-axis points in the correct direction. The update function listens for user input. If the ball is not yet launched and the spacebar is pressed, we launch the ball. If the ball is still not launched, we stop here. Otherwise, we generate a recast. A recast is an invisible line that will help us detect potential collision. Here, we draw a line from the center of the ball in the direction it is moving, with a length equal to the movement distance. If a hit is detected, we enter the condition. We propagate the onHit event if necessary, then query the collider object for specific components. If the brick component exists, the ball bounces off the brick. Calculate its new direction, call redirect, apply 1 damage to the brick, and apply acceleration to the ball. We can stop here. If the paddle component exists, the ball also bounces. But in the case of the paddle, we want the redirection angle to depend on where the ball hits the paddle. The closer to the center, the more vertical the redirection. The closer to the edge, the stronger the angle. Retrieve the new direction as a vector, redirect the ball, and call the touch function of the paddle. The function can stop here. Move the ball forward. Return to the editor, attach the component to the ball prefab, and fill in the available field. Then open the context, add a reference to the ball prefab, Add a function createBall that generates a ball and initialize it. Also, add a callback to the onDeath event that creates a new ball attached to the paddle if the first one is destroyed. Then go into load level and call the createBall function. Return to the editor, assign your ball reference, and click play to see the result. Now, a game where you can't lose isn't very fun. So we're going to add a net behind the paddle. Right-click on the Prefabs folder, create, scene, prefab, name it net. At the root, add a box collider moved by 0.5 on each axis. And as a child, a cube named skin, also moved by 0.5 on each axis. Right-click on the scripts folder, create, scripting, monobehavior script, name it net. Inside, define a reference to the skin and a color. In the awake function, simply apply the color you chose. Return to the editor, attach the component to the net prefab, and assign the exposed field. Open the context, add a reference to the net prefab, as well as a function createNet that instantiates the net at the given position and apply a specific size to it. In load level, call this function, making sure it is as wide as the level. Then go to the ball and add a new collision case. If the net component exists, the ball has hit the net. It is destroyed, and we propagate the onDeath event if someone is listening. Fill in the net reference in your context and click play to test the result. Now the base logic of the game is functional. We're going to add some game feel. If you remember what we said at the beginning, we will apply this visual effect to the skin children so we don't affect the gameplay logic. Before we start adding the visual game feel, what minigame or mechanic would you like me to tackle in the next tutorial? I'm looking for fresh ideas in the comments. Also, if this walkthrough has been helpful so far, a quick like goes a long way in supporting the channel. Thanks a lot for your kind support. Let's start by adding a jump and squash animation when a brick is touched. In a folder called Brick Animation, create a new monobehavior script and name it Brick Touched. Indicate that the brick component must exist on the object and expose an animation curve, a duration, and a strength. Also define some private variable, a reference to the transform component, whether the animation is active, when it started, the target offset, the starting position, and the starting scale. In the awake function, retrieve the brick component and the transform of its skin, which we use to initialize the starting position and scale. Also listen to the untouched event with a callback that triggers the animation. The reset function will be used to return the skin to its initial state. It stops the animation and restores the transform to its starting position scale. The animate function checks if the animation is already running. If so, it calls reset. Then it activates the animation and stores the current time. The update function immediately stops if the animation is not active. Otherwise, it calculates the elapsed time since the animation started. If we are in the first half of the time, move the skin upward, otherwise move it downward. Then, normalize the elapsed time, evaluate the result on the animation curve, and calculate the scale offset to apply. Apply the result. If the animation duration is exceeded, call reset to ensure the skin returns to its original state. Also, add an animation when the brick is destroyed. Create another component in the same folder and name it brick dyeing. Indicate that the brick component must exist on the object and expose an animation curve as well as a duration. As private variable, define a reference to the brick, the transform of the skin, a boolean to know if the animation is active, when it started, the target offset, and the starting scale. In the awake function, reference the brick component, the transform of the skin, and add a callback to the onDeath event that triggers the animation function. In the animate function, activate the animation, store the start time, the starting scale, and define the target offset as the inverse of the current scale. In the update function, if the animation is not active, stop immediately. Otherwise, calculate the elapsed time since the animation started, normalize it, get the multiplier by evaluating the animation curve, and calculate the offset to apply for this frame. Apply the offset. If the animation duration is reached, call die on the brick to destroy it. Add a final animation to make the brick light up when it's touched before changing color. Create another component in the same folder and name it brick light. Indicate that the brick component must exist. Expose an animation curve and half of the desired animation duration, since we first go to white before returning to the target color. As private variable, define a reference to the brick, one to the skin renderer, a boolean to define whether the animation is active, another boolean to know whether we are going toward white or toward the new color, when the animation started, and the three colors we need: the starting color, the illuminated color, and the final color. In the awake function, initialize the variable by retrieving the brick component, the skin renderer, and adding a callback to the untouched events that triggers the animation. The reset function ends the animation and forces the application of the final color. The animate function stops if the brick is immortal. If the animation is already active, force a reset. Then, store the start time, activate the animation, indicate that we are going toward white, retrieve the starting color, define the mid color, here slightly above white so that white remains visible longer, and the final color of the animation. The update function returns if the animation is not active. Otherwise, calculate the elapsed time since the start of the animation, normalize it, and get the multiplier from the animation curve. You need to determine color A and color B. If we are in the first half of the animation, A is the starting color and B is the intermediate color. Otherwise, A is the intermediate color and B is the final color. Calculate the color for this frame and apply it. Add a condition to switch animation phase, and if the animation is finished, call reset to ensure correct final values. Return to the editor, attach these three new components to the root of the brick prefab, and remember to fill in the exposed variable. You can run the game to see the result. We will add another animation, this time on the paddle. Create a folder paddle animation and create a new component paddle touched. Indicate that the paddle component must exist, expose an animation curve, and a recall strength. As private variable, define a reference to the skin transform, whether the animation is active, when it started, the impact normal, and the starting position. In the awake function, retrieve the paddle, the transform of the skin, the starting position, and a callback to the untouched event. The reset function ensures the animation is turned off and the skin is returned to the correct position. The animate function calls reset if the animation is already active. Then store the impact normal passed as parameter, the start time of the animation and activate the animation. The update function stops if the animation is not active. Otherwise, calculate the elapsed time since the animation started. If we are in the first part of the animation, move the paddle backward based on the impact point. Otherwise, move it forward. As always, if the animation is finished, call reset to restore everything. Return to Unity, attach this component to the root of the paddle prefab, and fill the exposed variable. We're going to finish by adding the tray that follows the ball as it moves. We'll also make this tray light up when the ball hits an obstacle. Create a folder called Ball Animation and a new component named Ball Moving. This one requires a ball component and a line renderer component to draw the tray. Expose a highlight duration, a color at the base of the ball, a color at the end of the trail, and an highlight color. As private variable, define a reference to the line renderer, a boolean that defines whether the tray is active, whether it is highlighted, and when the animation started. In the awake function, retrieve the line renderer, assign it a default material, and set a number of available points. You need a sufficient number to ensure you can draw a long path with multiple direction change. Define the start color and the end color of the trail, as well as the starting and ending weight. Retrieve the ball component and add a callback to its onHit event to trigger the flash, and another to the onLaunch event to activate the trail. The Activate Tracing function enables the trail and initialize all available points at the current position of the ball. The Flash function changes the starting color of the trail, activates the highlight boolean, and records the start time of the flash animation. In the Update function, immediately stop if the trail is not active. Otherwise, get the number of available points and shift all points by one index in the list. Only update index 0 with the current position of the ball to follow the trail. If the flash has been activated, calculate the elapsed time and compute the color to apply in order to smoothly return to the original color. Once this color is reached, mark the highlight as finished. Return to Unity, attach this component to the root of the ball prefab, and fill in the exposed variable. You now have a solid modular foundation for your Breakout game. The best way to master it is to take this base and try adding a unique feature. Maybe an extra wide paddle power-up, a multi-ball brick, or even more juice. If you found this useful, hit subscribe to join the Mojo crew. Meanwhile, if you're ready for your next challenge, check out this tutorial on making a snake game. It's the perfect way to keep that momentum going and build your portfolio. Thank you for building with me today, and I will see you in the next one.